Hey everyone, well, welcome to Lecture 13 for Chemistry 141. Let's take a look at Lewis structures. This is one of the ways that we can represent ions and atoms using just dots as electrons. And so what we do is we count up the number of valence electrons for an individual ion or atom, and we add the valence electrons singly for the first four. So we kind of put them at the 12, 3, 6, and 9 o'clock positions around a chemical symbol. And then if we have more electrons to add after those first four, then we can start to double up. So if we look at oxygen as an example here, we've got 6 valence electrons. It's got an electron configuration of 1s2, 2s2, 2p4. So we see those 6 valence electrons. We also could have got that 6 valence electrons by looking at the periodic table, seeing that oxygen is in group 6, and that tells us that we have 6 valence electrons. If we look at the electron dot structure for oxygen, it's going to look something like this. So we would put a dot here, here 2, here 3, here 4, and now I've got 2 electrons left, and so now I can start pairing them up. And so we'll take a look at that in class as well. Here are some examples for dot structures that we'll work out in class, but we'll look at sodium, look at fluorine, look at phosphorus, and look at neon. Now, in using those dot structures, we can use them to help us predict how atoms will bond in a compound, or at least how many bonds it will form in a compound. And so remember that atoms want to look like the noble gases, and we saw in that previous example, once we get through those examples, that neon has 8 valence electrons, as do all of the noble gases. And we call that an octet. And that's a term we'll use quite a bit, that atoms try to get an octet in their outermost shell. So we can use that dot structure of the atom to predict the number of electrons it will gain or lose in forming a compound. Forming ionic compounds. Now when two atoms such as potassium and chlorine come together, we know that we have a 1-to-1 electron transfer ratio. And we can see this fairly easily if we take a look at our dot structures. We start with our potassium here with 1 valence electron, and we've got our chlorine here with 7 valence electrons. And so what happens is this 1 valence electron comes over to here to chlorine, leaving us with potassium with a positive charge, leaving our chlorine here with a negative charge and forming a chloride ion. And we can see here that we've got that extra electron that came over there. Both of these ions now have an octet. For the chlorine, we can see its octet in the dot structure there. Now for potassium, it doesn't look like it has any electrons around it, but if we were to look at the previous shell, we would see that that was a core shell, and it is in fact filled, and that's what gives potassium its octet. But what if we don't have a 1-to-1 electron transfer ratio in our ions? Well, let's take a look at an example like that. Magnesium and fluorine are really a great example for that. If we take a look at magnesium, we see that magnesium has 2 valence electrons that it needs to try to get rid of. Fluorine, on the other hand, has 7 valence electrons, so it really only needs to gain 1. If we take a look at the charges that these metals would form based on their position in the periodic table, we see that magnesium tends to form a 2+ ion because it's a group 2. Fluorine tends to form a -1 ion. Well, we can't just put a 2+ and a -1 together because our charges won't cancel out. So let's take a look and see what happens. What we end up with for a formula for a compound forming between magnesium and fluorine is MgF2. So rather than just having one fluorine atom take 1 electron away from the magnesium, what we end up with is 2 fluorine atoms coming together to take 1 electron each away from that magnesium atom. So one of my magnesium electrons goes over here to this fluorine, makes that an F-. The other one goes over here to make that an F minus. It turns my magnesium into a magnesium 2 plus, and now I have two fluorine ions, each with a 1 minus. We always want to make sure that our total pluses and our total minuses balance so that they cancel out and we end up with a compound that has no net charge. So for magnesium and fluorine come together, when they come together, we're going to get a compound called magnesium fluoride with the formula MgF2. So how do we use those charges to determine the most likely charge? Or we've seen already how to determine the most likely charge for an ion using the periodic table, as long as it's an element that's in the main group. And using these charges, we can determine what the formula for an ionic compound is going to be that forms between a metal and a nonmetal. And what we do is we use the concept of lowest common multiple. You may remember this from some of your grade school days. Basically what we're doing is we're forcing the total pluses to equal the total minuses in an ionic compound. One example here would be strontium and fluorine, another sodium and oxygen, and another is magnesium and nitrogen. And we'll work these out in class. One of the concepts the book brings up, kind of a funny place, but it is an important concept when talking about ionic compounds, and this is the idea of lattice energy. And this is the energy that is released when an ionic compound is formed and we take those gaseous elements and force them to come into a solid. So we have gaseous atoms. First we turn them into ions, and then we bring them together as a solid. And we get a pretty substantial energy release there. And while a lot of people mistakenly think that it's because of that the electron transfer and making our atoms more stable as ions, that's not actually where we get energy release. The energy release comes primarily from taking gaseous atoms and condensing them down into a solid as ions. And so if we take a look at a graphic of that there, we have our sodium ions and our chloride ions there still in a gas form even after the electron transfer has taken place, and then they come together and form that solid there, and that releases a lot of energy. Now the larger the charges on the ions, the larger that lattice energy will be, just because of that stronger electrostatic attraction, the more energy that would have been absorbed to get them into the gas form, and then a stronger attraction as they come together in a solid is going to release even more energy. So if we had ions with a 2 plus and a 1 minus, that would be greater than a 1 plus and 1 minus. If I had a 2 plus and a 2 minus, that would be even greater, etc. As the charges go up, the energy that gets released when it becomes a lattice goes up as well. Let's talk about naming our compounds here. And whenever we do that, we use the term nomenclature. And when we use the term nomenclature, it means that we're systematically naming something, in this case chemical compounds. Now most ionic compounds we can fairly easily deduce from their name, since most elements form only one possible charge. This is certainly true with our main group elements, although even with main group elements there's still some that form more than one charge. We're going to learn how to deal with those at the end of today. Now, if an element can only form one possible charge, and we have two of those coming together, it means there's only going to be one way for those elements to come together to get a zero charge. Now, the transition metals always cause problems, and we're going to address those here in just a little bit as well. Now, one thing we need to be aware of also is that a lot of ionic compounds have been around and been known for a very long time, and so a lot of times they have common names like table salt. Table salt is really sodium chloride. Another example is baking soda. Sodium bicarbonate is its more appropriate name there. And so we just have to be aware that sometimes we run into names that don't necessarily agree with what we would name them by standard UPAC conventions, and so we're going to use those systematic names that are approved by UPAC. Now, when we're naming a compound, the first thing that we need to do is to recognize when we have an ionic compound, because ionic compounds are named slightly different than molecular compounds. We'll learn about molecular compounds in a later lecture. For ionic compounds, we just need to make sure we know when we have one. The easiest way to recognize an ionic compound is seeing that we have a metal and a nonmetal present. Once we know that we've got that, we want to identify the metal. Is it a main group element or a transition element? The reason we need to identify if it's main group metal or a transition metal is because our transition metals very often can form more than one charge, and we'll need to take an extra step in order to determine what that charge is. So just a very simple graphic. So first we identify that ionic compound here. Once we know we have an ionic compound, we want to know, do we have a transition metal that can form more than one type of ion, or do we just have a main group metal that can just form one type of ion? Let's take a look at the kinds that only form one type of ion. And anytime we have an ionic compound, we're going to focus primarily on binary ionic compounds. And we can identify binary ionic compounds because it means I only have two elements present. It doesn't mean I have two atoms present, but just two types of element present. So we name the compounds like this. We take the name of the cation, that's the metal, and we give it just its regular name. And then we take the base name of the anion, which is the nonmetal, and we add an IDE in a logical place. So if we take a look at some examples here, so NaCl, the name of the metal there is sodium, so we keep its name sodium. And now we have chlorine. We remove the INE, the ene, and we replace it with an IDE, so we have chloride. We have Mg3N2. That's not magnesium chloride. Let me correct that. This should be magnesium nitride. Okay, so we have Mg, which is magnesium, and then we have N, which is nitrogen, and nitrogen becomes nitride when it's an anion. Now we want to make sure that when you're doing that name that you're not putting that IDE in a funny place. Basically, my rule of thumb is if it sounds like it just rolls off the tongue, then it's a good name. If it sounds like you're going to get a cramp, then it's not such a good name. For example, we wouldn't want to call it nitrogide. That's not very easy to say. Nitride is very nice, easy to say, and so that's more than likely the correct way to do it. Let's go the other direction. What if we know the name of the compound and we want the formula? Well, we can do that with charges. Some examples here: calcium oxide. Well, if we look at calcium oxide, we know we have calcium. When we look at the periodic table, we see that calcium forms a 2+ because it's a group 2. Oxide means we have oxygen. Oxygen's a group 6, so when it forms an ion, it's going to form a 2-. How can we get a 2+ and a 2- to come together to cancel out? Well, that's just in a 1-to-1. So my formula between those two is going to be CaO. That's calcium oxide. There's another example, potassium sulfide. We'll work that one out in class. And aluminum bromide, we'll work that one out in class as well. We mentioned the transition metals just a moment ago, and they are a bit of a mess. And this is why, because many of our transition metals form more than one type of ion. A good example of that is iron. Iron can form either a 2+ ion or a 3+ ion. So when we say the term iron oxide, it could mean FeO if I have the Fe in a 2+ form, or Fe2O3 if I have the iron in a 3+ form. And we have to make sure that we distinguish between these two because they are very different compounds with very different properties. So if I specifically want the Fe2O3, I don't want to be grabbing the FeO off the shelf out of the stockroom. So since the name is not enough to define the compound, what we do is we add a Roman numeral to the name of the compound to identify the charge on the metal. And we put that Roman numeral directly after the name of the transition metal. So if we have FeO, we can figure out that that's Fe2+ and O2-. So we know that oxygen is always a 2-. And there's no net charge on there. Let me get rid of that there. try to write that a little better. I'll change colors here. So Fe we know is a 2 minus charge. So what do I need to have for the iron to get that to be neutral? Well, here the iron must be a 2 plus charge. So since iron now is a 2 plus, we call that iron 2 oxide. And the one thing that we need to make sure we understand is that 2 there does not indicate the number of irons. It does indicate the charge, not the number of them. What about Fe2O3? Well, here we have 3 oxygens. Now we know that oxygen has a 2 minus charge, but there's 3 of them, so I have a total of 6 minuses on the oxygen. With no net charge, it must mean that I have 6 total pluses on the iron, but there's 2 irons in there, and so each of those must have a 3 plus charge. So here the iron has a 3 plus charge, and so we call that iron 3 oxide, and again, this 3 here indicates my charge, not the number of iron ions in that compound. It's one of the most common mistakes we see made. So when we're naming our transition metals, we always have the name of the cation, so it's still iron here, and then in parentheses the charge of that cation in Roman numerals in parentheses, and then the base name of the anion. So we still name them the same way as we name our other ionic compounds. The only difference is we have that Roman numeral in there. Well, here are some examples that we'll work out in class, and you can work them out on your own if you'd like. We have lead 4 chloride. We have FeCl3, MnO2, and titanium 2 sulfide. Now with these compounds here, remember that that nonmetal will always have the same charge, and so you can use that to find the charge on the transition metal. Our last topic for the day is going to be polyatomic ions. So polyatomic ions are essentially molecules that have covalent bonds between the atoms. However, most of them needed extra electrons, or in one case it actually had to lose electrons, in order to form the necessary bonds. Because it gained extra electrons, or lost an electron, they ended up with a charge on them, and so they behave as kind of a superion, a very large polyatomic, many-atomed ion. And these are generally made up of nonmetals. We do have a couple that have metals in them. Now the easiest way to recognize an ionic compound that has a polyatomic ion in there is to see that we've got more than 2 types of element in the compound, and one of those is going to be a metal. We're still going to have a metal, non-metal concept here in general. However, we have more than 2 types of element in the compound. We do have some exceptions, with one of those being a metal, where we can actually have all nonmetals and still have an ionic compound, and we'll take a look at that in class as well. Well, here's your list of polyatomic ions from your book. You want to make sure that you're familiar with a lot of these, and because a lot of these are very common and they show up a lot in our compounds, and you don't want to have to look them up every single time that you see a polyatomic ion in an example. Let's take a look at some examples, and again, we're going to work these out in class. So we have potassium nitrate, iron 2 phosphate, Li2CO3. We see there that we've got 3 different types of atoms, so it's a good indication that we have a polyatomic ion. And then we have Cr2 SO4 3. And so there we have also 3 types of atoms in there, so a good indication that we have a polyatomic ion. You're certainly welcome to try those on your own before class or after class, but we will go through those examples during class time. Well, that finishes out Lecture 13. Hope you found all the information in here very useful, and as always, if you have any questions on any of this material, make sure you contact us.